Okay, well, thank you. Thank you for coming out. So yes, my name is Tom Offerman. We'll be talking about writing custom tracing functions. Just first, a little bit about me. So I live here in Portland, and I work here at New Relic. So my day job is helping our customers understand the performance of their Python web applications. Various places you can reach out to me on the internet. If you have any questions or comments or any feedback about the talk, I'd love to hear it. We may not have time for questions at the end, so certainly reach out if you have anything you want to talk about. So talking about tracing probably makes sense to take a step back and say, what is tracing? The definition I have up on the screen isn't necessarily a scientific definition, but this is kind of how I think of it, right? It's a way of surfacing the execution of your program, right? Understanding line by line what the Python interpreter is doing as it's running your program. Like, I almost think of it as this voice from the Python interpreter. It's like, Tom, I'm running line 1. Now I'm running line 2. I'm calling a function on line 10, right? So you're getting this very detailed view of everything that the Python interpreter is doing. If you've ever used the Python debugger, PDB, this may sound familiar, right? So PDB gives you the ability to step through your code one line at a time. And so tracing is very similar. But rather than having to push the S key to step through your code over and over again, tracing is going to do it automatically for you. And so why might you want to use tracing? Well, it kind of falls into this broad group of tools around debugging, around understanding your code, code exploration, introspection. That's really what it's best for. It's a standard part of the it's part of the standard library in Python, has been for a long time. So it's a useful tool in its own right. Kind of belongs in the same set of tools and techniques as, like, you know, if you're trying to understand how your program's working, you might add print statements or logging statements. You might use PDB. Tracing is a similar tool to solve similar problems. So it's useful in its own right. The other thing that I think is interesting about tracing is that understanding how tracing works gives you a glimpse into the internals of how Python works. So we'll be talking a little bit about that as well. Okay, so here's our agenda for today. We're going to be talking about some simple tracing examples. How does tracing work? Then we'll write some custom tracing functions. Talk about other projects that use custom tracing. And then we'll end with sort of a full-fledged example. Okay, if you do have any questions, there's some index cards up front. You can write them down and at them back, and we can get to them at the end. Okay, so we'll start with some simple tracing. And before we talk about how to trace something, we need something to trace. So I have a script here that's nothing too exciting, but it does have the virtue of being able to fit on a slide. There's a parent function. It calls a child function. There's some looping and some printing. Nothing too exciting. When you run it, you get output like this. So now if we want to trace this program, we can do it from the command line without modifying the code in any way by using the trace module. The trace module is callable. So you can invoke it with python-m trace. If you pass it the --trace argument and the name of the script, then you will get output that looks like this. You'll notice there are two different types of lines in this output. You'll see a line beginning with 3 dashes. That's going to indicate that a function is being called. And then you'll have lines, the remainder of the lines, which will show you the line number in the module and the source code of the line that's being executed. So you can see that, like, all of the code that you wrote that ran, every line of code corresponds to a line of trace output. There's more, obviously it doesn't fit on the slide. But it's also important to understand that it's not just your code that it is tracing. Trace is going to give you output for all code. It's going to give you, whether you're using a third-party package or whether you're using the standard library, all of it is going to be traced. So another simple example, we're going to make an HTTP request using the requests package. And this one is going to hit an endpoint that's going to return the 418 I'm a teapot status code. Gives you a nice little ASCII representation of the teapot. And so if we trace this one, same way, -m trace, we get similar output. This is the start of the output, and then if we kind of scroll to the end, you can see that the teapot there is in the end. And this is one kind of issue with using trace from the command line. The output of the trace is mixed in with the output of the program. It's all printed to standard out. When you're using trace, you start to get good at using tools like grep and other shell tools so that you can pick out the piece of information that you really want. If we grep for client.py, we can identify that, that we are in fact tracing lines of code from the standard library. This is the HTTP client.client package. This is Python 3.5. If we grep for API.py, we can see that this is requests code. So this may not be immediately obvious. You kind of have to know the code in question to be able to identify it. And one of the things we'll be talking about later on is a way to output additional information so that it's easier to identify what package a module belongs to. I haven't been showing the entire trace output on these slides. As you can see, it's really verbose, right? So we have this simple make a HTTP get, and somehow this is producing 250,000 lines of trace output. You can see by doing some shell scripting, putting together a little shell pipeline, what modules are called most often. So even though we are making a single HTTP request, somehow there's a lot of regular expression parsing, compiling going on. Again, another indication that it's not just your code, it's not just the third-party code that's being traced, but it's every single line of Python that's being run. So this may not be like immediately intuitive. I mean, like how can such a short program produce so much trace output? And the reason is that it starts tracing from the very, very beginning, and that includes the entire import process, right? We import requests at the beginning. It starts importing another series, a whole series of packages and modules. Every line of Python that's executed during that entire import process is included in the trace output. Now, oftentimes that's not really what you want. You want sort of more focused output, and so there's a way to do that. You can't do this from the command line, but if you use the trace class that's defined in the trace module, and then you use the runfunc method, you can pass in a function, and the tracing will only trace the running of that, the execution of that function. Right? If you can see, if you can run this, you get slightly more, you get considerably more focused results, a mere 13,000 lines of trace output. So that's kind of the simple case of tracing, right? It's built into the Python language, the standard library. It's always available. You can run it from the command line in its simplest form. You don't even have to modify any of the source code that you're tracing. It's extremely verbose, as we've seen, and you can also get more focused results if you use the trace class directly. All right, so let's talk about how tracing works. There are three main steps. Right? You need to have a tracing function. You need to register that tracing function. And then once you do those two, then the Python interpreter will run that tracing function before executing every line of Python code. So let's kind of go through the steps then to create a tracing function. We can use the one that's already defined in the standard library as a model. This is from the trace module. The trace class, like I said, is part of that. And there's a method local trace _ trace inside that. And that is what is being used, what's producing the line output. So I've modified it slightly so that it fits on the slide, but really it's not very much more complicated than that. And we'll kind of go through the different parts that make up a tracing function. So the first thing to realize that all tracing functions have to accept 3 arguments. All tracing functions also have to return a tracing function. So those are the sort of the 2 key parts of writing or creating your own tracing function. So let's try and figure out what these arguments mean, what they're all about. So the first one is a frame. And that's where we get a little bit into, let's talk about how the Python interpreter works, right? What is a frame? So when you've got source code, like here we have a function defined, the Python interpreter doesn't run it directly, right? It compiles it into bytecode, which you can see a representation of at the bottom of the slide. And internally, it stores the byte compiled code inside of a code object. And then it stores the code object inside of an execution frame, a frame object. Right, so the frame object is a way that the Python interpreter keeps track of where it is, what line it is inside the function, keeps track of the local and global variables that are available in the function. Each time a function is called, a new frame object is created, and each time a function exits, that frame is removed, disappears. And then internally, Python keeps all of these frames on a stack, right? So when you enter a new function, you create a frame, it gets put onto the stack. When the function exits, the frame is destroyed, and it is popped off the stack. So that's kind of a quick summary of what the steps I just described. That may all seem a little bit abstract, but luckily there's this awesome tool online, this web application called pythontutor.com, which does a really good job of letting you visualize what the stack looked like as you execute Python. So it has a text box where you can enter in a Python script or program, and then it lets you step through it line by line, and it can show you the frames created and destroyed on the stack, right? And so if we take that parent-child script that I was showing earlier, right, you can see we start out with a global frame. Once we're inside the parent function, we have created a new parent frame, and it gets pushed onto the stack. The parent calls out to the child function, creating a new frame, right? That gets pushed onto the stack as well. Eventually, the child function returns. That frame disappears. We go back to the parent frame. And when it returns, the parent frame is removed, and now we're left with the original frame. So frames are objects in Python, which means that we can take a look and see what's inside them. There's a method called _getFrame in the sys module, and that will give you the frame object for the currently executing frame. And if we run help on that, we can see all the different attributes that are stored on a frame object. All right, we can see that we have a reference to the parent frame, or the function that called this function. We can see the globals and locals defined. Globals and locals defined. We can see the code object for the code that's being run inside the frame. Right, and that's right. Code objects are objects too, right? And so we can take a look and see what's inside of a code object. Right, and here we can see the number of arguments that are passed into the code object or the function. We can see the name of the file where the function was defined. We can see what the name of the function is. Right, and so this frame object and the code object sort of nested inside of it, that's all available to a tracing function to be able to sort of access and pull out interesting data on. The other two arguments to a tracing function don't require quite as much explanation. There is a y argument and then a third argument at the end. The y is often called an event as well, and that's a string that basically describes what type of execution is happening inside the frame. Right? So when you first call a function and you first enter a frame, that is going to be the call event. Every subsequent line of code that's run inside that frame is going to be a line event. When the function returns, return event. If it happens to throw an exception, then you have the exception event. The third argument isn't always defined, but on a return event, you get access to the return value. In an exception event, you get access to the exception that's caused. The exception. And so all of this, and so the events are key because it allows your tracing function to perform different actions based on where what type of execution is happening inside the frame. Right? If we look back at this local trace method, we can see that it's checking what type of event it is and deciding whether to perform some action based on its align event or to just do nothing. You can see that it's pulling out data like what line number of code is being executed, right? And you can access that from the frame object. It can dig into the code object that's part of the frame, and it can get the file name of where the function was defined. So those three arguments really allow the tracing function access to all the information it might want about the code that is currently executing. Right, so that explains the tracing function, and then the next step is you have to register it. And there is a function in the sys module called setTrace, and if you pass a tracing function into it, that lets the Python interpreter know that you would like all code to be traced with this tracing function. And what that means is the Python interpreter will run this tracing function before the execution of every line of Python code. So if you remember, the tracing function also returned a tracing function, and that might seem a little strange, right? Like if you have this tracing function that could run before every single line of code, why would you need to return another tracing function? And the reason is because you can have multiple tracing functions, and sometimes that's valuable. Sometimes that capability is important. Usually they're kind of broken up into a system tracer and a local tracer. And a system tracer is one that runs when you first enter a function, right? When the frame is first created and the call event fires. The function that's returned from the system tracer is the local tracer, and that's the one that runs for every subsequent event in the frame. Then when the new frame is created, we sort of start all over again. The system tracer fires for the call event, and then the local tracer for the remainder. If you remember this slide talking about the frame attributes, you may have noticed at the bottom there's an f_trace attribute, and this is where the local tracer is stored, right? So when you're not at the call event, but you're in one of the subsequent events, the Python interpreter is going to run the tracing function that is stored in this frame. And that happens automatically when you return a function, return a tracing function from your tracer. So maybe an example of kind of stepping through it might help. Here we've got two tracing functions. We've got the system tracer and a local one. The return value for both is the local tracer. And here we have sort of an example script where we're going to call two different functions. So when does each tracer run? Well, when the count1 function is first called, right? That is a call event. And so the system tracer is going to run. It's going to return a function, the local tracer, that's going to get stored on the frame. And then for each subsequent event, the line event and the return event, it's that local tracing function that's going to run. Exiting that function, now we're going to start a new frame, a new function. So again, it's the call event that's going to run the system, the registered system tracing function. It's going to return the local one, and then each subsequent event is going to run that local one. This is also convenient because sometimes you're in a situation where you only want to trace the call event. You only want to run a tracing function when you first enter a function. And you have this ability, but basically if you have your system tracing function return none, then that means that no tracing function will run on any subsequent events. It's only the call events that's going to get a tracer run. So to recap, for tracing to work, you need to have a tracing function. It needs to have the signature where it accepts 3 arguments. It needs to return a tracing function. And then you need to register it with the sys.setTrace. All right, so far we've been talking about the one that's already defined inside the trace module. So let's write some of our own custom tracing functions. And the first one, we're going to try and address some of those problems that we talked about early on, right? So remember when we ran the tracing of the teapot.py, we had the mixing of the output of the program with the mixing of the trace output. So we're going to see if we can solve that problem. And then the other problem we were talking about is that it wasn't clear which like we could tell what module was running, but we couldn't tell what package it belonged to. So here is one that will solve both of those problems. Here we can get the full file name, the full path for the module. And rather than printing to standard out like the built-in one, we can instead use logging so that we can separate the output of the program from the logged trace output. So I haven't shown the logging configuration here, but you can imagine that you can have the logging going to an entirely separate file. Right, and so here we run the same thing, and then we grep through the trace.log file that we produced. You can see clearly that client.py does indeed belong to the HTTP package in the Python 3.5 standard library. It's also clear that API.py belongs to the requests package. All right, another example is let's write a tracing function that will capture the arguments that were passed into a function every time a function is called. Right, so in this case, we only care about the call event. So we only care about the call event, so we only have to worry about that. And the way we're gonna access this information is that there is a co_argcount attribute on the code object. That's gonna tell us the number of arguments that were passed in. The co_var names gives you the names of all of the arguments and the names of the locally defined variables. So we will just slice off the beginning so that we can get the ones that are the arguments. And then we'll go ahead and look up the values in the locals dictionary on the frame. Right, so here we've got two different functions. One that takes an x and y argument, the other one, same x and y, but it has default values. And when we use our trace call args tracing function, we can see that we're able to pick up both. So there's another way that you could pass arguments into a function, right? You can pass a variable number of arguments and keyword arguments using the star args and star keyword args. And so if we use our same trace call args tracing function, this is the output that we get. Not quite as useful. For some reason, that doesn't work. So we have to go back to the drawing board and think of a different approach. And it turns out that this co_argcount that we were relying on to tell us how many arguments were passed into the function doesn't actually handle the variable case, doesn't handle the star args and the star keyword args case. But there's another solution. When you realize that when you create a function, when a function is first called and you create a frame, so you're in the call event, the only variables that are defined in locals at that point are the ones that are passed in as arguments, right? So we can just take a different approach and get them that way. We can just loop through the locals available in the frame object, and then we can print them out. So let's try our new tracing function, trace call args2, and here you can see we're now getting the values for args and keyword args. So those are just a couple of examples of how you might write your own tracing function, some of the problems that maybe you can solve with tracing. And there are a lot of other projects out there that use same or similar techniques. If anybody has used coverage.py and calculated what percentage of their code is covered by their test suite, basically, this entire project is based on tracing functionality that's built into the standard library. If you look in coverage.py's source code, you will see two definitions of two different tracers. There's a pure Python one, there's a one written in C for better performance. And if you look at the Python tracer, it should look very familiar, right? It accepts the familiar 3 arguments, it's switching on the event, and it's returning a tracer. The Python debugger itself is built on top of BDB, which is described in the Python docs as the debugger framework. And BDB uses tracing, right? It has a trace dispatch method, same familiar 3 arguments, switching on events, and returning functions, right? So BDB and PDB all based on this trace functionality that's built right into Python. And even the pythontutor.com example that I was showing you earlier, right? That is based on BDB as well. And so under the hood, it's using the same tracing functionality that we just described. Okay, let's talk about kind of a bigger example, right? Up until now, we've been talking about tracing, and we've noticed that it produces a whole lot of output, very verbose. It's all text-based, but sometimes it might be nice to get a different representation of trace data. It would be nice to have sort of a more graphical visualization. Building those kind of tools isn't really my specialty. So when I started thinking about a trace visualizer, I was thinking like, well, what else is out there that I could kind of borrow or steal and use to visualize something? So I was kind of picturing something like this, right? In Chrome DevTools, you have this this waterfall timeline view of how long things take. And I was looking at that and I was thinking like, well, that would be a cool visualization if you could see like how long each function took and understand sort of the calling relationship, sort of the parent-child calling relationship throughout it. As part of my day job, being familiar with web application performance, I'm familiar, there's another tool, open source tool out there called Zipkin, and it has a similar waterfall timeline visualization. And it turns out that that's a little easier to work with. So the plan here is we're going to try and use this UI, but sort of hijack it so that it is displaying it's visualizing trace output rather than what it was originally designed for. I think it's helpful to understand the original purpose of the tool before we use it, so we'll just talk a little bit about what Zipkin is. It's designed for distributed tracing of microservices, for visualizing that. Right? If you picture a web service, it receives a request, and before it sends a response, it may make database queries, HTTP calls to other APIs. It may do a lot of different things behind the scenes before it sends back that response. And Zipkin is a way of visualizing that. So each of those database queries, each of those RPC calls are considered spans, and then the entire collection of spans that happen in the course of generating a response, that is a single trace. All right, we can walk through an example and give you a chance to admire some of my awesome Keynote graphics wizardry. So here we have a web application. A browser user comes to it, sends a request. So the web application has received a request, and it starts a red span. It makes a call out, queries the database. The database has received this query, and then the database sends back results. So it's received and then send. That completes that blue span. Next, the web application may call out to an API endpoint. API endpoint receives that request. But before it sends back a response, it in turn makes another call out to Redis, starting a new span. Redis receives this request, sends back the response, right? That completes the magenta span. Now we can send back the response from the API to the web application. That closes off that ends the green span. And then finally, you can return the response back to the original user. Right? And all this in its entirety is a single trace representing that original request and response that was sent from the web app. So that those spans could be represented in a diagram that looks like this. All right, we've got the web application span is the longest, kind of the root or the parent span. Underneath it, there's a separate span for the database query, for the API call. And you can see underneath the API call, there's this child span for the Redis operation. Right? And this kind of diagram is exactly what I wanted for tracing a script. Right? We can translate a trace for a web request response is just like running a program. And rather than a span representing an RPC call, we can have it represent a function call, right? So a function can be called, that's like receiving a request, and then it can return, and that's like sending the response, right? And it would translate just like this. All of these spans between function calls rather than RPC calls, and then we can have a very similar diagram. In order to submit data into Zipkin, there are a number of different ways, but it has a REST API, and you can represent spans as JSON. Kind of going through it, down here you can see this is a server request. So this is like the kind of JSON that would be sent to represent a function being called. Every span has a unique ID. You need to keep track of who called it, what the parent span ID is, and you want to keep track of the trace ID to represent so that Zipkin can group all of the spans together. So that's kind of the plan, right? We're going to trace a program, we're going to log results, then we're going to convert those logged results into a format that Zipkin understands, and then we can hijack the Zipkin UI to visualize that trace. So because I need to keep track of these span IDs that are associated with every frame, I decided to do it as a single object with a span IDs attribute, right? So I can keep a dictionary mapping frame to span IDs. And you can see I've decided to make it callable, where you accept the frame event and arguments, and then I have separate tracing methods to handle the start of the function, the call event, and the return event as well. If we look at the trace call, we can see this is where we generate the span ID for this particular frame, and then we store it away in the span IDs dictionary. And then we're going to log 5 pieces of data to in CSV format. Right? We're going to log the current span ID, the parent span ID, the name of the function that's being called. We're going to log a timestamp, and then this is a call, so it's like the equivalent of a server receive. Right? On the flip side, when the function returns, we're going to run this trace return function, and we're going to log the same things: the span ID, what's my parent span ID, the name of the function, timestamp. Only this time we're going to record SS for server sent. Right? So calling a function is like server receive. Returning from a function is like server sent. We've got this helper method here to look up the parent span ID. Right? Basically, you can access the parent frame inside your current frame and look it up. And then when you run this, you produce a log file that looks like this, right? Comma-separated values, where you have the span ID, the parent, and all the things that we talked about logging. So then it's really just a matter of converting this into the JSON that Zipkin expects. So I have a log to span program. The essential logic is in here, right? We're going to loop through the CSV file. We're going to submit each line to a make span function, and then we're going to send that span into the Zipkin collector. Right? Make span is you pass the arguments in, and you create the span object. And then send span is going to know how to take that span object, turn it into JSON, and then send it to the Zipkin API. And then the end result of this is that you get the visualization just like Zipkin uses for distributed tracing, only now it's displaying a visualization of the tracing of the program that I just ran. So I think that's kind of an interesting approach because I didn't actually have to write very much code, right? Really, I was using the tracing capability that's already built into the Python standard library, using this already existing open source tool and borrowing their UI. And so with very little code being written on my part, you get this really interesting visualization of the execution of this program. So hopefully you've kind of gotten a chance to see how tracing works, how you write your own tracing functions. There's nothing too scary about writing them. It is something to realize that tracing can be extraordinarily verbose, so you definitely want to think about ways to either narrow down what you're tracing or get really good at grepping through trace logs. You have the ability to do really deep introspection, right? Because you have access to that frame object that we talked about. You have access to the code object that's being executed. And lastly, you don't have to write your own UI. You can always find someone else's to borrow or steal. I'm going to post all of the code examples used in this talk on GitHub. That's where you can find it. The code examples are already up. I'll also post the slide deck in PDF form That's not up yet, but that'll be up shortly. And that's it. Thanks so much.